This last year's given us all time to reflect, and what I've realized is that science is a lot like celebrating Jewish holidays, particularly Passover. It involves asking really good questions and a lot of suffering. And while the data that I am going to present didn't involve wandering in the desert for 40 years, sometimes it felt like it. In the spirit of Passover, today I will ask 4 questions. When a leaf falls in the river, who comes with it? Do leaf types affect pathways of energy flow? How does this study differ from all other studies? And when will we meet again in person? And like a Seder, science should always tell a good story. So let's start with our peanut butter and cracker analogy, which stream ecologists love. The crackers like the leaf, dry, unpalatable, not delicious. But when you spread it with the peanut butter, the microbes, they start the breakdown process and make it more nutritious. But let's unpack the analogy. We know riparian zones are diverse and different leaves function differently. So we can improve our analogy just with adding a lot more different types of crackers. But this year of contemplation made me realize that the leaves and crackers really aren't the same. Unlike the leaf, the cracker was never alive. The leaf used to be alive, and even though it's dead now, the 100 or so bacteria and fungi that are living inside this dead leaf are very much alive. I think I need that first glass of wine. Okay then. If we sequence the microbes on dead leaves, we find that they come into the river with very different assemblages of both bacteria and fungi. So leaves aren't like crackers, they're really more like flying microbiomes. And if you let me extend the analogy of the microbes to candy, leaves enter rivers looking more like this, each with their own set of microbes. Which begs the question, are these initial differences important? Or are the microbes on the leaves, when they enter the river, do they get quickly replaced by aquatic microbes? On one hand, microbes in decomposition might be strictly aquatic, like fish, but on the other hand, they may also have terrestrial stages like aquatic insects and amphibians. With standard molecular tools, you can tell who's there, but you can't tell if they're doing anything. And microbes dig dormancy. Microbes can hang out and do nothing for very long periods of time. Finding endophytes on decomposing litter just means they're on the team roster. It doesn't mean they're in the game. So we've developed a new tool called quantitative stable isotope probing, which differentiates growing from dormant microbes. So this is a big advance in microbial ecology. How does it work? Well, it turns out that all organisms, including microbes, when they replicate, take in oxygen from water. So if we grow microbes in water that's enriched with 18O, we can trace the heavy isotope into the microbes that are growing. But the difference in weight isn't very big. You can't measure it on a bathroom scale, or on any scale for that matter. You need to do it through a centrifuge in cesium chloride. If you grow microbes in normal water, they have different weights based on their nucleotide composition. Let me demonstrate. If we had a microbial community with just 4 taxa, we would start with our blue peanut M&Ms. We would also find a closely related sister taxa, the orange peanut M&Ms. We might find yellow plain M&Ms, which are related but a little more distinct, but still part of the M&M family. And then we could also find distantly related good and plenties. If we were to take these taxa and put them in a centrifuge and spin it, we might end up with something like this. They would distribute based on their weights. The blue ones weigh the most, the orange ones weigh the least. But if we were to grow the same community in 18O, we might find this. So let's unpack it. First thing you see is that the orange taxa didn't move at all. They're not growing. Neither did the blue taxa. The yellow moved a little bit, so they're growing slowly. But look at these pink. They grew good and plenty. They took up a lot of the 18O isotope, meaning they're growing a lot. But to get this data, we need to sequence 15 layers in this tube and 15 layers in this tube. More suffering. I think I need that second glass of wine. Then we plot all the species on a graph to measure how much of the 18O isotope is taken up. The further to the right, the more growth. If the error bars overlap with 0, no growth. But real life is more than just a bowl of candy, and it looks more like this, with thousands of taxa, each with their own error bars. Don't worry about the legend. It's color-coded by phylum and lists taxa. I'm showing it so that you can feel our pain. QSIP's hard. For this experiment, we incubated 4 leaf species in stream water and sediments in laboratory mesocosms and harvested at 2 time periods to generate growth plots for both bacteria and fungi. The results. Most fungi found on submerged litter enter with the leaves. Most bacteria colonize from the water column. The patterns hold across both leaf types and harvest dates. But what about the growers? Even more pronounced. Most of the active fungi on submerged leaves entered with the leaf. Most of the active bacteria, in contrast, colonized from the water column. And now, for a moment of zen. On the left are the fungi and the numbers are species. The blue circles show what enter with the leaves, so look at all those big numbers. The other 2 circles show what's active at the 2 harvests, and you can see there's only 8 growing species that entered from the water column. And when we look at what came in with the leaf, more species are actually active later in decomposition, the second harvest, suggesting that they waited out until conditions are right for them. The bacteria show the opposite. Very few taxa came in with the dried leaf, but hundreds colonized from the water and grew. And for bacteria, if we look at total growth, measured as the 18O summed across all bacterial taxa, we see that it increases over time, supporting the idea that bacteria become more active as decomposition progresses. So to summarize part 1, when a leaf falls into the river, what comes with it and what colonizes it? Most of the bacteria are strictly aquatic, like fish, but most of the fungi are like aquatic insects with a terrestrial stage. The peanut butter colonizing the cracker is a good analogy for the bacteria, but the fungi operate more like these pretzels, where the filling's on the inside. On to question 2. Once the leaf starts decomposing, where does it go? Do different leaves go different places? We know they decompose at different rates, but is the carbon and nitrogen bound in leaves from different species go to different pools? There are 4 major options. Some of the compounds escape right away, like tea in hot water. And our work's shown that leaves from different species leach different compounds, and in general, faster decomposing litter types leach more than slowly decomposing litter. The second option is our microbes, the peanut butter and the candy, and we now know that they get a big head start on decomposition. We've got our macroscopic food web, the invertebrates and the fish that get the nutrients by either eating the leaves directly or eating the microbes that eat the leaves. And the fourth option is the compounds that are so unpalatable, not even the microbes want to eat it. And these compounds get stored in the river sediments. And I liken them to the boxes of old matzo from Passover's past, which accrue in my pantry because, well, truth be told, I never make it the whole 8 days eating unleavened bread. Strictly observing Jewish holidays is even harder than QSIP. It's a good thing Jews don't believe in hell. Okay, let's just focus on the microbes and the insects. The microbes are supposed to help the insects. That's what got this whole peanut butter and a cracker analogy started. But the analogy falls apart because the peanut butter never eats the crackers, but the microbes eat the leaves. So microbes are both beneficial to insects, but they can also compete with insects for the litter. Our second question, does leaf type affect the amount of carbon and nitrogen that flows to insects? We grew different trees with isotope labels so that we could trace carbon and nitrogen while the leaves are decomposing. We incubate leaves in the river just like everyone else, but we can trace the carbon and nitrogen molecules as they move through the food web. I'm going to summarize 10 years of data. We started with 2 species, but reviewers wanted more. We went to 4. They still wanted more. Finally, we ended up with 12. We suffered into truth. I'm going to need that 3rd glass of wine. Oh, just give me the bottle. Across these 2 experiments, 2 patterns emerge. First, microbial biomass is almost always higher on faster decomposing litter types. Second, in contrast, assimilation of carbon and nitrogen is almost always higher in slower decomposing litter types. Let's look at the data. This summarizes the 4 species experiment. Mass loss is on the bottom. On the top is microbial CNN. Both are higher on the 2 fast decomposing litter types. Next is the caddisfly packs, and then the community packs. In both cases, CNN assimilation by invertebrates is higher in slowly decomposing litter types. Same pattern for the 12 species. Microbial biomass increases with decomposition rate. Assimilation of carbon and nitrogen by invertebrates shows the opposite pattern and is higher in slowly decomposing litter types. Before I drink my 4th glass of wine, let's review. Manishtana. How does this study differ from all other studies? This is the first study to demonstrate the importance of leaf endophytes in aquatic decomposition, suggesting that an amphibious lifestyle may be the rule rather than the exception for fungi. And second, we showed that leaf litter type affects element flow through food webs. Fast decomposers shunt their carbon and nitrogen to microbes, but slow decomposers are fueling macroscopic food webs. I'm going to open the door for Elijah now, but if he shows up, somebody needs to make sure that he pays his registration fee. Mazel tov, we survived another virtual meeting. Next year in Grand Rapids?